Uh, so Professor Xiaokui is a faculty member in the School of Computing at the US. His research focuses on data management, especially on data privacy and algorithm for large data. He recently received the Best Research Paper Award in VLDB 2021, and he's also a distinguished member of ACM. He obtained a PhD in computer science from the Chinese University of Hong Kong in 2008. So I personally know Xiaokui for a long time. So I know he has been working on data privacy for almost 20 years. He's a really expert in this area, and he has also done a lot of good work in social network. So we are looking forward to your talk. So
Thanks a lot for the very kind introduction, and it is my great honor to present in this seminar series. So my talk today will focus on a problem called statistical database. I'll first explain what this problem is and why it is non-trivial and important. And then I'll talk about the existing solutions for the problem, as well as our recent research effort on this problem that followed a road less traveled, that is to use synthetic data. And in the end, I'll conclude the talk with some future directions. We are now living in an era of big data, and it is becoming easier and easier for various organizations to collect large volumes of data about individuals. Oftentimes, the organizations may have a need to share the data they have collected with some third party for various purposes. For example, it might be a hospital that has collected some medical records from the patient and wants to share information from the medical records to some researchers for a study. Or it can be one department of a company that has collected some user behavior data and wants to share information from the data with another department of the company. In this kind of data sharing scenarios, it's quite apparent that we cannot just share the raw data directly, right? Because the raw data will contain a lot of sensitive information. So certain measure has to be taken to protect the privacy of the individuals involved in the data. So one approach for this problem would be to use a statistical database. So this is a kind of database that does not reveal the raw data to the users, but only allow them to ask aggregate queries. The rationale is that aggregate queries can allow the user to learn some pattern of the data, but they will not directly reveal the specific information of specific individuals. But of course, you can imagine that if somebody asks a series of aggregate queries, it might still be possible for him or her to just look at the aggregate query results and infer some specific tuple in the data. So because of that, usually a statistical database would also have some additional defense, such as returning only noisy answers instead of exact answers, or denying queries whenever they are deemed unsafe. But even with all of these additional measures, it is still non-trivial to ensure privacy protection because there exists some very powerful attack that can be used to reconstruct the underlying data from query results, even when they're noisy. This was demonstrated in a Paul's paper that was published some 20 years ago. So what this paper showed is that when we have a set of count query results on a table, that even when those query results are noisy, it is still possible for us to reconstruct a portion of the underlying table based on the noisy count queries. And the basic idea is that those noisy count query results can be converted into some linear constraints about the underlying data. So if we take all of the count query results into account, then we have a linear program. And then by solving the linear program and do some necessary rounding, we can infer the values in the underlying table. There are some very interesting theoretical results demonstrated in that paper, but the basic idea is that even if each count query has a substantial amount of noise, we can still reconstruct a large portion of the input data using just a polynomial number of queries that are randomly constructed. So this is a very powerful attack in a theoretical sense because it only requires random queries. It doesn't even need the queries to be well structured. But of course, you may wonder how practical this kind of attack is. Well, the US Census Bureau had the same questions recently. So they tried this attack on the census data that they released 10 years ago. And in the end, they found that this attack was able to re-identify the data from around 17% of the US population. So it's not just a science fiction, it's a real threat. Attacks like this has motivated a long line of research in the database community on how we can construct a statistical database with rigorous privacy protection. And the state-of-the-art solution or utilize a privacy notion called differential privacy. I'll talk about the concept of differential privacy later, but the basic idea is that this is a formal privacy framework proposed by theoreticians, and it can enable us to precisely quantify how much privacy loss we will have when we answer a query with a certain amount of noise. So under this framework, a statistical database can be constructed in the following manner. So we start with a predefined privacy budget, right? And then every time there is a query coming in, we're going to evaluate the privacy cost that we will incur by answering the query with a certain amount of noise. And then we just keep track of the total privacy cost that we have when answering queries. And whenever the total privacy cost exceeds our predefined threshold, we just stop the database, turn it down, and allow nobody to access it anymore. So the big advantage of this approach is that since it's built upon differential privacy, it offers a very strong degree of privacy protection against a very wide spectrum of privacy attacks. So we no longer need to worry about the kind of attacks that were demonstrated in the Potts paper and so on. So this is a very attractive guarantee. And also there are a lot of interesting research problems that we can investigate in this kind of framework. First of all, for each query that we receive, we need to have a way to figure out how much noise we should inject into the query result in order to have a good degree of privacy protection, right? Calculating this noise amount is in many cases quite non-trivial because the user's query can involve a lot of tables in a very complex manner, okay? So there are research looking into how we can compute this amount of noise as accurate as possible. And then in addition to the computation noise, the computation of the noise amount in terms of accuracy, we also need to think about the efficiency of this computation. I mean, you can't afford to receive a query and then spend 10 days to figure out the right amount of noise to add and then answer the actual query in 10 seconds, right? So we also need to make the estimation of the noise amount efficient enough. And finally, once you have an efficient and accurate method of estimating the noise amount, you need to figure out how it can be integrated into the existing data management system to make it work seamlessly in the query processing pipeline. So there are a lot of interesting research problems to look into. But what we observed is that solutions in this line of research have a common problem. That is, the statistical database would become unusable after the privacy budget is depleted. So you can have a statistical database that is on for 3 days, and then just because it received a lot of queries, the privacy budget is over, and then you have to shut it down forever. From a user experience perspective, this is just not that appealing. I mean, usually user would expect the data to be always there for them to ask a question whenever they want, right? So to address this issue, we would like to consider a different route towards building a statistical database, and that is to use synthetic data. So the basic idea is that given an input data set, we do not directly build a statistical database on it. Instead, we're going to generate a synthetic version of this data sets that mimics the original one. And then we're going to use this synthetic version of the data to answer whatever queries that a user may ask. We do not impose any limits on what types of queries the user want to ask and what is the number of queries that we can answer. And the reason that we can afford to do this is because whatever information the user can extract from their queries would be confined by the information that is in the synthetic version of the data. So as long as the synthetic version of the data is generated in a way that satisfies a very strong notion of privacy, such as differential privacy, then we don't need to worry about what sets of information the user can extract from their queries, because whatever they can extract would be from the synthetic version instead of from the original version. So that is to say, using synthetic data to build a statistical database is like inviting the user to an all-you-can-eat buffet. Okay, we pay a one-time cost of generating the synthetic data, and then the user are invited to ask an unlimited number of queries as long as their stomach are not full. Furthermore, we do not need to make any change to the database management system because we just need to load the synthetic data into whatever database that we want, and then we can start answering queries. And we don't have any additional query costs either, because processing query on the synthetic data will be the same as query processing on the original data. But there is a downside. The downside is that we don't really have an accuracy guarantee for the queries that we answer. I mean, for some queries, our synthetic data may offer an answer that's quite accurate, but for some other queries, our answers could be far off. And that is just unavoidable because, as demonstrated in the pause paper, we cannot afford to answer too many queries too accurately. In contrast, using the approach of injecting noise directly into query answers to build a statistical database is like inviting your friends to a fine dining restaurant. So depending on what queries the users may ask, you may deplete your pricing budget very quickly, and then you just cannot order any more dishes. Furthermore, we need to pay a lot of costs to change our database management system to incorporate the noise injection mechanism. And we also have additional computation costs per query. But the good thing is that if we do it this way, then it is possible for us to provide an accuracy guarantee for each of the query that we answer. And that is because we know exactly what is the distribution of the noise that we're going to inject and what is the variance of the noise that we're going to inject. So we can provide this kind of information to the users so that they can kind of derive a confidence interval of the query results. In contrast, if we use a synthetic data approach, then we cannot provide this kind of confidence interval. Okay, so you can see that these two approaches strike different trade-offs between the availability of the database and the accuracy of the query results. We are more interested in the synthetic data approach because it has its unique advantages and it is less studied in the literature. So there are a lot more interesting problems that we can investigate. So in what follows, I will introduce our recent efforts on building a synthetic database building a statistical database using synthetic data. And I'll start with a quick introduction of differential privacy and then talk about how we generate synthetic data under differential privacy. Okay, so differential privacy is a notion of privacy proposed by theoreticians back in 2006. Over the years, it has become more and more popular, and it has now seen mainstream adoptions by Apple, the US censors, and so on. The formulation of differential privacy borrows idea from cryptography in the sense that it models privacy protection as a game against the adversary. So in what follows, I'll first use a toy example to illustrate what this game actually is, and then we'll talk about the formal definition of differential privacy. So just imagine that we have a data set. Let's call it D. And let's say in the data set, we have some individuals' information, including Alice. And now consider that we construct a slightly different data set, D prime, by removing Alice information, right? So we have two very similar data sets, except that Alice information is only present in one of them, but not the other. Now, suppose that we randomly pick one of these two data sets and extract some information from the chosen data. And then let's say we pass this piece of information to an adversary and ask the adversary to guess whether the information is extracted from D or D prime. So here's a question. If the adversary is unable to tell whether this piece of information is from D or D prime, what is the implication on Alice's privacy? Well, the implication is if the adversary is unable to tell, then Alice's privacy should be considered preserved by this piece of information O. And that is because if the adversary is unable to tell whether Alice is in the data set or not, then there's much less the adversary can say about the private information of Alice. So this is a rationale of differential privacy. It aims to ensure that whatever information we release from a sensitive data set, the information will not enable an adversary to infer whether a particular individual is in the data set or not. And by doing so, it ensures that the private information of any particular individual is protected. More formally, differential privacy requires that whenever we want to release some information from a data set, that piece of information has to be generated using a randomized algorithm, say A. And that randomized algorithm must satisfy the inequality here. So let me explain. Central to this inequality, we have a ratio of two probabilities. The probability above is the probability that when we feed a dataset D to this randomized algorithm A, the algorithm gives us a piece of output O. And then the one below is the probability that when we modify the dataset by removing one individual's data and then feed the modified data to the same randomized algorithm A, the probability that we get the same piece of output O. And such pair of datasets that differ in one individual's information is referred to as a pair of neighboring datasets. So what differential privacy requires is that the ratio of these two probabilities should be bounded by e to the power of epsilon from above and e to the power of minus epsilon from below. So when epsilon is reasonably small, it basically says that this ratio should be not too far away from 1. So that would mean when an adversary observes this piece of information output by the algorithm, it will be difficult for the adversary to tell whether the input is a dataset D or its neighbor D prime. So that would be consistent with the rationale that we have just explained in the last slide. That is, by preventing the adversary to tell whether a certain individual exists in the data or not, we can guarantee privacy protection for the individual. And notice that differential privacy requires that this inequality here holds for any pair of neighboring data sets and any output of O. So this just to avoid any lack of privacy protection for any individual or for any possible output of the algorithm. So here I have another illustration of the definition of differential privacy. So I have a figure here, and the x-axis of the figure represents the possible output of this algorithm A. And the blue line here represents the distribution of the algorithm's output when the input is a dataset D. And the red line here represents the distribution of the algorithm's output when the input dataset is a slightly different dataset D prime. So what differential privacy requires is that these two distributions should be similar to each other everywhere, in the sense that when we pick an arbitrary output of the algorithm and look at its probability in the two distributions, we should find that the two distributions the two probabilities should have a bounded ratio of at most e to the power epsilon. So that is how differential privacy is defined. I guess a question that you would immediately have is, how can we achieve such a complicated notion of privacy, right? Well, there is some standard way to achieve that. So a canonical approach would be to take a non-private algorithm and then look at which component of the algorithm actually need to access the input data. And for those components, what we can do is to inject some noise into it to randomize the choices made by those components. And then by carefully deciding what noise to add and how much noise we should add, we can satisfy differential privacy. There is a whole set of formal theory behind this choice of noise amount and noise distribution, but I will not go into the details. Okay, so that's the quick introduction of differential privacy. And now I'm going to talk about how we can synthesize relational data with differential privacy. And I'm going to start from the simple case when we have only one table to consider. So let's say we have a table like this. It's a very simple table with only two attributes, right? Age and whether or not the individual has diabetes. And let's say we want to release a synthetic version of the data that's in a way that satisfies differential privacy, right? In that case, what can we do? At the first glance, it's not very clear how we can inject noise into this table because we have some categorical values such as yes or no, and some different options of age such as below 30 and so on and so forth. So it's not clear how we can inject numeric noise in this kind of categorical type, right? But there's a very simple way to get around it. What we need to do is to first convert the data set into a set of counts. And then we just need to add noise into those counts to achieve differential privacy. And then we can map the noisy counts back to a synthetic table. For example, given this particular table here, we can first convert it into a frequency matrix. So this frequency matrix would have the same dimensionality as the number of attributes in the input table. So each dimension corresponds to one of the attributes here. And each entry in this matrix will correspond to a combination of attribute values in the original table. So this particular entry here will correspond to the combination of below 30 and has diabetes. And the value of the entry just equals the frequency of that value combination in the input data. So it's a one-to-one mapping between the table and the frequency matrix here. Now, once we obtain this frequency matrix, adding noise becomes quite simple because now all we have are a bunch of numeric values. So we just add noise into those values, and that in a way can satisfy differential privacy as long as we choose the noise amount and the noise distribution appropriately. After that, we just need to map this noisy matrix back to a table, and that will be our synthetic table. And the mapping is also straightforward. So for example, here we have a noisy value of 2 plus x0. And to generate the synthetic table, we just need to round this noisy value to an integer. And let's say if the rounded integer is 3, then we just need to generate 3 synthetic tuple with age under 30 and has diabetes. And that's it. That's a simple example of how we can generate synthetic data under differential privacy. But there is a problem here. The problem here is that if we really want this approach to work, then this frequency matrix cannot have too many entries. But in practice, if our input data set has a sizable number of attributes, then the number of entries in this frequency matrix can actually be huge. And that is because the number of entries in the matrix will be exponential to the number of attributes in the data. You may wonder why it is a problem to have too many entries there. Well, think about it. If the number of entries in this matrix is prohibitively large, then we don't even have a way to materialize all of the entries in the matrix. And if we do not materialize all of the entries in the matrix, then there's no way we can add noise to all of them and generate synthetic data accordingly. So that's the first problem. The second problem is, even if we can somehow afford to materialize all of those entries, the values in the matrix is going to be extremely sparse. Like most of them will be 0 or 1. When we have such a matrix, such a sparse matrix, adding noise to the matrix would basically destroy all of the signals that we have in the matrix. And as a consequence, if we generate synthetic data based on such a noisy matrix, the synthetic data would also be useless. So that is the main problem of this simple approach of synthetic data generation. So how can we address this problem? Well, our observation here is that in practice, the attributes in a data set are usually correlated with each other. And whenever that happens, the intrinsic dimensionality of the data set can actually be much smaller than the number of attributes in the data. So that motivated us to exploit the correlations among the attributes to mitigate the sparsity issue that we just mentioned. So based on this observation, we developed a method for generating synthetic data under differential privacy called PriBase. And the basic idea of this approach is as follows. Given a table with a sizable number of attributes, we do not directly convert it into a frequency matrix and then add noise into it to generate synthetic data. Instead, what we do is that we first decompose the table into a set of low-dimensional table. And then we look at the frequency matrix of each low-dimensional table and generate its synthetic version. After that, we use the noisy low-dimensional tables to reconstruct a noise table with all of the attributes present. The advantage of this approach is that since we are working with low-dimensional tables instead of high-dimensional ones, the signal in these low-dimensional tables will no longer have the sparsity issue. So we can afford to add noise into them without destroying the signal in the table. So that mitigates the main deficiency of the simple approach that we have just mentioned. But of course, in order for this approach to work, we will need to ensure that the decomposition of the original table into the low-dimensional tables do not lose too much information, right? So we need to have an effective way to do the decomposition and an effective way to do the reconstruction. And for these two steps, we use a Bayesian network. Intuitively, a Bayesian network is a graph that captures the correlation among the attributes in the input data. For example, let's say our table has 5 attributes A, B, C, D, E. Then the corresponding Bayesian network for this table could be something like this. So each node is an attribute in the input data, and each edge between the nodes indicates some kind of dependency among the attributes. For instance, here we have C having 2 incoming edges from A and B. So that indicates that C highly depends on A and B, and it is conditionally independent of the other attributes when A and B are given. So similarly, the other edges in this Bayesian network will indicate that E depend on B and C, and D depend on A and E. So in a way, this is kind of like the functional dependency that we have in relational databases, just that the dependency is much weaker here. It kind of indicates a correlation instead of a total dependency. And because they are quite similar to functional dependency, we can also use them to decompose the table in a way that is similar to a database normalization. So for example, given the 3 dependency that we have here, we can decompose the original table into 3 smaller tables, ABC, BCE, and AED. So each of these tables will correspond to one of the dependencies above. Okay, so that's how we can do a decomposition of the table using a Bayesian network. And the intuition here is that the decomposition can capture the most significant correlation of attributes in the original table. And that's why the decomposition is good in a certain sense. And once we have this decomposed tables, we can add noise into them to generate a synthetic version. And then we can use them to reconstruct a full data set, again, using the dependencies that we have in the network. For example, let's say we want to generate a synthetic tuple T with all 5 attributes values. In that case, we can first look at the table T1 here, and then examine the distribution of ABC values in the table. Okay, you can basically treat it as a distribution of ABC, and then we can just sample a combination of ABC value from this distribution. So that would be the ABC value of our synthetic tuple. So what remains to do is to figure out what are the E and the D values of the tuple, right? And for that, we can look at the other 2 tables. In particular, if we want to figure out the E value of the tuple, we can look at this table here and then infer a conditional distribution of E given B and C from the table. Once we have that conditional distribution, we just need to sample E from that conditional distribution based on the B and C value that we already obtained. So that filled in another blank. And we just need to carry on this process and look at the 3rd tables, and then we can fill in the D value of the tuple. And that will finish the construction of one synthetic tuple. So you can imagine that if we repeat this process again and again, then we can have an arbitrary number of synthetic tuples that we want. So that's how we can generate synthetic data from such kind of a decomposed noisy tables. So you can see that it all hinges on the availability of a Bayesian network. So now the question is, how can we actually construct such a Bayesian network? And keep in mind that our construction of the Bayesian network will need to satisfy differential privacy. Otherwise, we cannot guarantee that our whole process of generating synthetic data is compliant with BP. For that, we can't directly use any of the prior solutions for Bayesian network construction because they were not designed with differential privacy in mind. So what we did is that we developed our own solution by borrowing idea from a classic approach by Xiao and Liu, and we inject noise into the algorithm to achieve differential privacy. So our algorithm works as follows. Let's say we have D attributes in the input data. In that case, we'll start with an empty Bayesian network. And then we consider some attribute combinations. For each attribute combination, we're going to look at the last attribute in the combination and evaluate its correlation with the other attributes in the combination. Okay. In particular, we'll evaluate the mutual information between them. And the larger the mutual information is, the stronger the correlation would there be. So we just evaluate a number of possible combinations of the values, and we choose the combination with the maximum mutual information. And then we add the corresponding dependency into the Bayesian network. So that's our first step. After that, we're going to repeat this process to look at the other candidate combinations of attributes, and then recursively or iteratively choose the one with the maximum mutual information, subject to some constraint that a Bayesian network would have. Okay, and that's it. It's a very simple algorithm that utilizes the mutual information as the criteria for choosing dependencies. Now the question is, how can we make this algorithm differentially private? But the intuition here is that to make it differentially private, we just need to figure out which part of the algorithm need to access the input data. And then we need to randomize the choices made by that part of the algorithm, right? Then by looking at the algorithm here, you can see that there's only one step that needs to access the input tuples, and that is the evaluation of mutual information. So what we did is that we inject noise into the mutual information before selecting the best attribute combination amongst the one that we consider. So the rationale here is that by adding noise into the mutual information, the choice made by the algorithm will no longer be deterministic. Okay, sometimes it may choose the best one, sometimes it may choose the second best, and so on and so forth. And in terms of utility, this is not too bad either, because as long as the noise amount is not too large, the choice made by the algorithm won't be too bad. And in that case, our Bayesian network will still be okay. So in summary, our approach works by first constructing a noisy version of the Bayesian network using a variant of the child approach. And then using the Bayesian network, we obtain a low dimensional decomposition of the original table. And we generate a synthetic version of the low dimensional table and use them to reconstruct a synthetic version of the input data. Subsequently, we devised an improved approach based on a different graphical model. So we do not use Bayesian network, but use something that is related called a Markov random field. And the main advantage is that by using a Markov random field, we can have more flexibility in terms of the choice of low dimensional marginals. So I did not talk about this previously when I talk about the prime base, but the basic idea is that in order for the low dimensional tables to form a Bayesian network, there are some constraints that the low dimensional tables should obey. And that actually restrict the choice of our low dimensional tables. In prime base, we no longer have those constraints. So that enable us to choose a better representation of the original data. And that in the end leads to much better synthetic data. Recently, we used prime MRF to participate in the Differential Privacy Algorithm Challenge organized by the National Institute of Standards and Technology, and it became the winning solution. So that's how we can generate a single table using differential privacy. Now I'm going to move on to the more interesting case of generating multiple tables. So just imagine that we have a database that contains a number of tables, and some of them are private and some of them are public. Okay. For example, if you have a database that contains some information about products and individuals, then the table concerning products itself would be public tables, whereas the table concerning which individual has purchased which product would be considered a private table. So how can we synthesize a database like this? A naive idea is just to synthesize each private table separately, say using our private MRF algorithm. But the problem here is that if we do it that way, then we can't really correctly handle the foreign keys among the tables. And let me explain why. So in census data, very often we will have two tables like this. We have a table containing information about individuals. And then we have another table containing information about households. And apparently there will be some foreign keys from the individual table referencing the household table to indicate which individuals belong to the same household. All right. Now, just think about a common case like this and think about how we can use private NRF or any single table synthesis algorithm to generate synthetic version of the data. So what we can do for each of this table is to synthesize them separately. So that will end up with a bunch of synthetic individual and a bunch of synthetic household. But then we will need to figure out a way to identify the foreign keys, right? We need to assign individuals to households in a way that actually makes sense. But that's not easy. I mean, if you just do a random assignment, then you may end up with some households that do not look real. Like you may have a household full of children with no adults and so on and so forth. Okay. So we need to have a way to make sure that the assignment actually makes sense. And one intuitive way to do this is to augment the household table. Like in addition to whatever attribute the household table already has, we also add in some attribute to indicate what is the size of the household, what is the average age of the member in the household, what is the number of female members in the household, and so on and so forth. Okay. And then we will generate a synthetic version of this augmented version of household. And after that, we can utilize these augmented attributes in the synthetic table to help us decide which individuals should belong to which household. Okay, so basically we need to do a bipartite matching with all of those aggregate information as constraints. But even this approach still has a lot of problems. First, if the individual table has a sizable number of attributes, then you can imagine that the number of attributes that we need to add into the household table would be quite large, right? Otherwise, you have to drop some of the attributes from the household table, and that will lead to a problem. For instance, if you dropped the average age here, then there's no way you can ensure that the assignment of individual to household will still obey the constraint on age for each household. Okay, so that's the first problem. If you want to add all of the attributes as augmented attributes into the household table, then household table would have a huge dimensionality. That would immensely increase the difficulty of data synthesis. Furthermore, even if you are somehow able to create all of these augmented attributes and synthesize them, it is still difficult to match individual to households. Because basically what you're dealing with would be a bipartite matching with multiple matching criteria on size, on average age, and so on and so forth. And such a problem is NP hard in general. So it's not easy to come up with a good matching. To address this problem, our idea is to not directly use any augmented attribute, but to consider that there is some latent variable in the household table that's invisible to us, but it decides the type of each household. Okay, and then this latent variable would also decide what are the members in the household. So in that case, we just need to deal with this latent variable instead of dealing with a large number of augmented attributes. So basically, we consider the following generative process for households and individuals. We first sample the latent variable from a certain distribution. And then based on the sampled latent variable, we sample the size of the household as well as its attributes. And then given the latent variable and the size of the household, we sample a given number of individuals. So assume that this is the process of generating households and individuals. Accordingly, we define the likelihood of a household with a size S as follows. And for simplicity, I'm going to omit the household attributes for the time being. So we consider that the likelihood of this household H will be decided by the likelihood of the latent variable times the likelihood of the household size given the latent variable, as well as the product of the likelihood of each individual given the latent variable. And we take a sum of this over all possible choices of latent variables. So that is how we model the likelihood of a household. So now the problem becomes, given a set of households that we observed, how can we estimate the distribution of the latent variable, as well as the distribution of the household size given the latent variable, as well as the conditional distribution of individuals given the latent variables? And this can be addressed by using a graphical model to model the observed data. And that graphical model would have some latent variables incorporated. And the way to estimate all of these things that we want is to use expectation maximization. So that is kind of an extended approach to deal with latent variables. But in our setting, we also have the additional constraint of differential privacy. So we just add noise into this expectation maximization algorithm to satisfy the requirements of VP. Okay. So in the end, what we have is an algorithm that works as follows. Say we have an individual table and a household table. Then we're going to first take the individual table, okay, look at the information there and look at which individual belong to the same household, and use our expectation maximization algorithm with differential privacy to obtain a model of the individual attributes as well as the household type, namely the latent variable. Okay. So effectively, this would give us an augmented attribute in the household table. Okay. And we will also have a model that captures the relationship between this household type and the individuals. So that would be our first model. And apparently, this first model does not cover everything yet because we haven't considered the household table's attribute, right? But what you can observe here is that all that need to be covered is just the household attribute itself as well as the household type, and they are all in the same table. Since they are in the same table, we can just invoke our previous algorithm for single table synthesis, and that would give us a model of household and its type. Okay. So once we have these two models, we can start to generate synthetic household and synthetic individuals. The idea is that using this model, we can sample synthetic households and their types. And then by feeding the household type into the second model, we can generate synthetic individuals for any given household. So that's how we can handle the case of two tables with one foreign key. And now we can discuss how this two table algorithm can be extended for more general cases. For example, what if we have a foreign key train? Like we have a sequence of tables and each table would have a foreign key pointing to the next table. Well, in that case, we just need to apply our two table algorithm following the order of the foreign key. So we can start from the first table, okay, figure out a latent variable that would decide the grouping in the first table, okay, and use that latent variable to augment the second table. And then we just treat this augment table as a whole, and then use it to figure out a type of grouping in this second table, and use that latent variable to augment the third table, and so on and so forth. Okay, so that's how we can easily deal with a foreign key training. As another example, consider the case that we have a reverse stack schema. So for example, say we have an individual table in the middle, and then we have a table on the left that captures the education records of each individual. And then we have another table that captures the medical records of each individual. Okay, so the two tables on the left and the right would have foreign keys referencing the individual table. In that case, we can first look at the education table and then use our two table algorithm to figure out the type of education records for each education record group. Okay, and then we can look at the medical records and do the same to figure out what is the type of medical record grouping that each individual has. So that would lead to an individual table with two augmented attributes. And then we can just apply our single table synthesis algorithm on this table in the center, and then we're done. So in general, we can apply the two table algorithm to handle the case when each private table has at most one foreign key, and when there's no cycle in the key references. Okay, so whenever these two conditions are satisfied simultaneously, we can always organize a private table in something like a tree. Okay, and once we have this kind of tree structure, we just need to start from the tables in the bottom. Okay, use them to augment the tables one layer up, and then do it again and again until we reach the root. And once we reach the root, we just need to apply the single table algorithm on the root, and then we're done. Okay. So in our experiments, we use some census data available from IPUMS. And the table that we have includes one person table that has 500,000 tuple, and one household table that has 250,000 tuples. And each of these tables has quite a number of attributes. So we generate synthetic versions of this table, and then we consider some count queries on the tables concerning both households and individuals. So the query will look something like this. Like how many households have annual income larger than a certain threshold, and at least one member with age larger than 30. So the characteristics of this kind of query is that we have one range predicate on a household attribute, something like this. And then we have one or more predicates on individual attributes, something like this. And the query predicates are randomly generated. And we measure the accuracy of the query result by the relative error of the query result with a normalizing factor to mitigate the influence of query results that are very small. Okay, so we ensure that the denominator here is at least 0.5% of the total population. And in this case, it's going to be 0.5% times 500,000. Okay, so these are some of the representative experimental results that we have. So the blue line here represents the query error that we achieved when the data is synthesized using our two-table algorithm. And so that's the blue line. And the green orange line here represents the query error that we have when we use private MRF, namely the single table algorithm, to synthesize each table individually. And then we assign individuals to households in a random manner while ensuring that the size of the household is correct. Okay, so what you can see is that the error of private MRF is actually much larger than the error of the two-table approach, simply because the private MRF approach cannot correctly capture the correlations among the individuals and the households. Okay. So in summary, synthetic relational data is a promising approach for constructing a statistical database because it can support unlimited amount of queries, and it doesn't require any change to the database management system. But the main challenge, as we see now, is that handling foreign key is quite non-trivial. We have some preliminary results in this aspect, but we have barely scratched the surface because there are a lot more problems that need to be addressed before we can declare victory on addressing this problem of using synthetic data to support a statistical database. So here are a few problems that we think are very important, but we don't know how to address yet. So the first is the case when a private table has multiple foreign keys. So just imagine that we have an individual table, okay, and we have a company table that records which individual works for each company, and then we have a household table. Now, when we have a case like this, it's rather difficult to generate the synthetic data because the foreign keys kind of interfere with each other. I mean, intuitively, we may first sample households and then sample household member, but then we need to figure out how those household members should be mapped to companies. And if we start from company table, then we're going to face the same problem when we need to produce a household table. Of course, intuitive idea would be to somehow combine company and household at the same time in the synthesis of the individual table. But it is just that we haven't figured out a very good way to do that. Okay, so that's the first problem. The second problem that we don't know how to address is the case when a private table has some relationships to itself. So for example, we can have an individual table and then another table that records which individual is a friend with another individual. The main difficulty in this case is that whenever we have two tables like this, essentially there is an induced network of the individuals. And whenever there is a network like this, the synthesis of the data should be able to capture the topological information in this network in one way or another, right? So for example, if the original network has some community structure, then it would be ideal that the synthetic data would also have similar community structure and so on and so forth. But right now, we don't really know how to do that. And now just imagine that you have a complex network with of pirate tables with all of these foreign key constraints that cover the two difficult cases that we have just mentioned. Then we don't even know how to start. And besides that, if we go beyond relational data, we can see that there are a lot other types of data that could benefit from synthetic data generation. So for example, we may have time series, we may have trajectories, or we may have market basket data. So how to generate minimal synthetic data for those data types under differential privacy, it's still not very well addressed. With this, I would like to conclude my talk, and I would like to acknowledge my co-authors for the work that this paper is based upon. Okay, thank you, and I'm ready to take questions.
Thank you so much, Xiaokui, for your super clear presentation and a very impressive work.
Thank you.
Yeah, so if you have any question, you can either raise your hand or you can post your question in the chat box.
Yeah, Xiaokui, thank you so much for the really wonderful talk. So I have one question. But the idea of integrating the statistical model in the this noise adding is brilliant. At the same time, how can we make sure such knowledge is correct, or how can we measure how good the knowledge is to help you to add the noise? To be specific, for example, at the prime Bayes method, if my Bayesian network is not that perfect in whatever sense, and how can I detect that? Or how can I measure the goodness of a Bayesian network for this purpose? And later at your latest part, when you have the latent variable, is there any hints or any indicators I can see that, oh, indeed, there could be more than one latent variables that I cannot see?
Yeah, so we don't have very good theoretical results on how to quantify the errors that we may have from a Bayesian network or from the latent variable approach that we mentioned in the second part. But what we can do is to use some empirical evaluation, like after you have a graphical model constructed in private manner, that you can use a query workflow to evaluate what is the query result that we will obtain from this model versus the result that we obtain from the original data. And then sort of take a look at how different the query results actually are. And if they are vastly different, then you know that the Bayesian network or the graphical model is not that good. So as I mentioned in the beginning part of this talk, this kind of synthetic approach has a major drawback that is not easy to provide an accuracy guarantee for the query results. And that is an limitation that it'd be wonderful to address, but we don't know how to address yet.
Thank you.
Thanks.
Hi, Xiaokui. I have a question.
Yes.
Thanks for the wonderful talk. I'm just wondering how you could handle some updates to the database in the sense, because nowadays we have all these online settings where your underlying data table can be constantly updated. How do you handle the incremental case? Do you handle in the batch mode, or do you handle in online fashion? And how would it affect the efficiency of all your solutions? Thanks.
Okay, so right now our solution only considers static data. If there are updates in the data, then we need to run from scratch.
I see.
So ideally, it would be good to have some approach that can incrementally update the model to generate synthetic data. But currently, we don't know how to do that. And also, updates in the data is actually very difficult for any differentially private approach, because intuitively, if you only have a static version of the data, then the change of one individual is going to change maybe one tuple in your input. But if you're talking about updates, then you can imagine that changing one individual, we're changing a whole history of updates. So that's just a lot more changes to handle in differential privacy. So
I see.
Yeah.
Yeah. So could that also be a source of attack? Because attackers can probably, disguise as one of the data provider and use the updates, the change to compromise the solution.
Yeah, that could be a concern. And if we really want to deal with this kind of attack, then one way is to divide your budget among different versions of the data release. Like instead of you having an epsilon of 1 for each of the release, you're having an epsilon of 1 for all of your data release combined. So in that case, even if an attacker utilizes multiple versions of the release data, you are still covered.
Okay, thank you.
Thank you.
So there's a question maybe related to what Jian has asked. So from Tong, the question is, thanks for the wonderful talk. Could you elaborate a little bit on the theoretical property of DPEM and DPEN?
Yeah, that's a very question. In fact, we don't have any strong theoretical results in the DPEM and facial network. And the main difficulty is that in general, it's difficult to to formulate some sort of optimality guarantee when you have a Bayesian network or the EM approach, even when we do not have noise, right? And when you add noise into the mix, the problem even becomes more complicated. I mean, in the machine learning literature, there are a lot of research looking into how SGD would perform when there's noise in each iteration. And even in that kind of simple cases, the guarantee is kind of loose, right? So for our case, it's even more complicated, and we don't know whether it is possible to derive very interesting or very strong theoretical results in that aspect. Yep.
Okay.
So may I have one more question?
Sure.
Yeah. So when you produce the synthetic data, you have to use kind of like a distribution estimated from the real data. Right. And we know one thing is that the data distribution or the data existence is far from even. That means maybe in a large data space, you have some part, you have enough data to produce a good enough density estimation. But in many other places, particularly when the dimensionality is not that low, let's say over 5 attributes, you may not even have enough data there to produce to estimate the distribution very well. And this will be particularly challenging when you try to preserve the joining keys, because you need to connect different pieces together. Do you have any comments or any advice or say, well, what should be the right way to tackle this issue?
Sure. So I would say you're basically saying that what do we do if some part of data is very sparse?
Yeah.
If that under the current framework of differential privacy, if some part of the data is very sparse, then that part of data has to be disregarded.
Okay.
Like because differential privacy tries to protect inference against whether a certain individual exists or not. And if some part of data is so sparse that only 1 or 2 tuples exist in that large region, then it basically means that that piece of information is too sensitive to be released. So under the framework of differential privacy, that has to be disregarded. So another question is, what if we really want to sort of preserve those kind of information? Well, in that case, I would say we need to change the privacy definition, like change differential privacy in a way to make it more lenient to those sparse part of the data. But how to do it in a way that is meaningful and also well accepted, it's a problem.
Thank you.
Thank you.
Yeah, thank you.
We have another question from Hui Tian. The question is Laplacian noise used in adding noise? Is there any other noise used to generate your table to guarantee DP?
Yeah, sure. So generally, we can use Laplace noise to achieve pure DP, namely epsilon differential privacy. And you can use Gaussian noise to achieve epsilon delta differential privacy. And there are other noise distribution that you can use depending on which flavor of differential privacy that you go for. And specific to our method, in prive base, we have used Laplace. And in prive NMF, we have used Gaussian, because Gaussian noise allow us to have better composition properties, if you know what it is. So, and then in the latent variable approach, we also use Gaussian noise, because there are just quite a number of places that we need to add noise into, and we want the overall privacy guarantee to be as tight as possible. And that's why we use Gaussian noise, because it has an advantage when it comes to the composition of the privacy guarantee of multiple components.
Okay. Is there any question? Okay, so thank you very much, Xiaokui,
Thank you.
for coming to our event. And
Thanks for
thank
having
you
me.
everyone for attending the talk. Okay.
Thank you.
Thank you.
Okay, bye-bye.
Have a nice day. Thank you, Xiaokui. Yeah.
Thank you.
Thank you. Bye.
Thank you. Bye-bye.
Bye-bye.
Bye.